Lesson 3.1, exponential functions and their graphs. What we should learn: how to recognize and evaluate exponential functions with base A, how to graph exponential functions with base A, recognize and evaluate an exponential function with base E, that's a natural log, and then how to do real life problems. So let's start here, right? What's an exponential function? It's a function with an x as the variable as an exponent, hence exponential function. So that's an exponential function. What do they look like? Well, the best way to do that is by example. So we have this function f equals 2x. We're going to do -2, -1, 0, 1, 2, and then I guess 3. All we're going to do is sub it in like we always do, right? So here's my x, plug that in, get my y. Let's start with the easy ones down here first. So 2 cubed, 2 to the third is 8, 2 squared is 4, 2 to the first is 2, 2 to the 0, anything to 0 is 1, that's not 0. 2 to the -1, remember negative power flips the base, so it becomes 1 over 2. And then 2 to the -2, same idea, 1 over 2 squared, which is 1 over 4. So if I plot these, we got -2 and 1/4, -1 and 1/2, 0 and 1, 1 and 2, 2 and 4, 3 and 8. With a graph, doesn't look like this. A couple things here I want to point out. There's no vertical asymptote, but there is a horizontal one. You know, I didn't show here. I could have done like -10, and you got 2 to the -10, which is 1 over 2 to the 10, which is like 1 over a big number. You never get a negative value, so it never goes below 0. You actually can never be 0. So there is a horizontal asymptote at y equals 0. So that's an exponential graph looks like. It grows very fast and doesn't cross the 0 line. So that was with the base of 2. It does change if it's a different base, but it just kind of grows faster or slower. So this is what an exponential graph looks like. And particularly when the base is bigger than 1. That's called a growth. So when I give you a graph that's like this, where the base is bigger than 1, call that, and it has an asymptote at y equals 0, you can't cross. We cross at 0, 1 on the y-intercept. So that's like a basic graph looks like that. Now, much like everything else, this is like our parent function. And then from there, we can move it, right? Anything on the outside, that's right here, moves it up and down. But also, that is the horizontal asymptote. HA is at y equals k. Because when there's nothing there, right, like I did up here, it's at 0. So when you have nothing there, it's 0. If you move it up and down, that's this horizontal asymptote. So k is how much you move it up or down, but it's also the horizontal asymptote. No, we don't have a vertical one. The inside, h right here, that's to move it left and right. So you move your graph left to right from there. A is the orientation and shape, so like how much of a curve does it do? But really what I use it for is the initial y-intercept. This is before we do a vertical shift. So to recap, right? If we're doing a growth graph, that means our b is greater than 1, right? That's when it's a growth. Our graph should kind of look like this. Like that. Now a couple key points here, right? This right here, the asymptotes, is at y equals k. If you don't have a k, it's 0. That's the default here. And our initial y-intercept, this guy right here, that's our a. So whatever a is, that's how far up you go. So in this case, there was no a, it was a 1. So across that 1. The one we did up here, right? There's no a, there's no number in front to 1. So it crosses that 1. So that's your initial y-intercept. That's your horizontal asymptote. And then it's a growth, so it goes up. So let's practice some. So the first one here, I'm gonna find all that stuff. We're gonna go, my a is 1, right? Because there's no number in front of this. That's not my a, that's my b. My b is greater than 1, so it's a growth. And then we're going to move up 1, which is also our r, so we're going to go up 1, right? But that's also our horizontal asymptote at y equals 1. And then we're going to go right 2. So I tend to graph this part first. So this is like a basic one, so we know what we're talking about. Right, my a is 1, it's a growth, so it looks something like this. Like a nice little basic graph, right? Now we're going to have asymptote at 1. So I'm going to move my graph up. So I'm going to draw my little asymptote at 1. Like that. Right. My a is 1, so I'm going to go 1 above that right here. That's where normally what I would cross. Like right there would be my y-intercept, right there, right? But we can move it right too. So I already moved it up 1. That's what this guy was. That's the asymptote. And then I would be 1 away from that because my a, and then we have to move it right 2. So it's 1, 2 right here. That's where it would be. That's like my normal y-intercept. So it's kind of like how we bend and go up this way. Now it's going to bend and go up right here. Like right here, it's kind of like it starts bending up. So it looks something, I'm doing purple. So it looks something like this. And that's our graph, right? If I was doing domain, we'd negative infinity, positive infinity. Range would be from 1 to infinity. Next one, 4, 0. So same idea. A is 1. B is greater than 1, so it is a growth initially. We'll talk about that. And then plus 0. So my y-intercept, my horizontal asymptote, is at y equals 0. So y equals 0. Right here is my asymptote. My a is 1. We're going to cross that 1. And this 4 is going to go up. So I'm going to draw the normal one first. So this is like a normal one. Right? Nothing's much changed. It looks like that. What does the 4 do? It makes it grow a little faster. We're doing a sketch. It's not that important. The difference between 3 and 4 is negligible. It just makes it kind of grow faster. Like a 1 would kind of go slower like this. Or actually 1 wouldn't grow. 2 would grow slower. A 10 would grow really fast. So it's just a sketch. I just care about the general function. Okay. What about the negative? Well, that is on the inside. So it's a horizontal flip. Remember, inside affects the x's. So it affects the x, and x is left and right. So it's on the inside, so we're going to flip it left and right. So it's going to go down like this. So this graph's actually what we call a decay graph. Because see how the graph is going down, you're decaying. Like if that was like your money in the stock market, it's like that's, oh no, 1929. Let's move on. So speaking of exponential decay, look here, right? Here's the decay graph. What's the difference? Your b starting off, well, besides the fact that you're going down, your b starting off is less than 1. Your b starting off is less than 1, it's a decay. Everything else works the same. So if you understand how to graph a growth graph, you're gonna know how to graph a decay graph. Just you start off with this picture instead of this picture. That's what happens when the base value is less than 1. So let's do a few examples. So like here, y equals 3/5 x. I don't have graphs here, that's weird. My a is 1, so I'm gonna cross that 1. Right, there's the plus 0, so my horizontal asymptote is at y equals 0. And then my b is less than 1, so it's a decay to start off. It can always change with the flip, but to start off, it's a decay. So like that. That's a graph, decay graph. If I was doing this one, right? So here's my graph again. My a is -1, but I'll just consider it 1. Well, our a is 1. The negative is just a flip. Don't worry about it for everything else. So a is my 1. We're gonna go left 4, sorry, and my horizontal asymptote, nothing there. Is that y equals 0. So again, I always like to draw the basic graph first before I move it. So we kind of have this. Like here's my asymptote. I would cross that 1, and it would be a decay graph, right? Because 3/5. So it looks like this. It looks like the graph we just did. Let me do dotted. So like that. Now we got to do a couple things. Got to move it left 4, and then we got to flip it. You're technically supposed to flip it first. So what's this flip? It's on the outside, so it's a vertical flip. Right, remember outside, y, follow. Anything on the outside affects the y, so we're gonna flip it up and down. So it's called an x-axis flip. I always think about it as like a vertical flip. So we're gonna flip it up and down. So it's gonna look kind of like this. Right, we flipped it up and down. But then you gotta move it left 4. So you're always supposed to flip first and then you move it. So flip, and then we gotta move it left 4. So normally I would cross right here at -1. By the way, notice how a was -1. That's why I crossed there. But then we can move it left 4. So 1, 2, 3, 4. Right here's where I'm actually. Right here's that same point. So we're gonna do the same graph. When we hit that, we're gonna kind of like bend toward, get close to the line. And that's that graph. Let's do one more, kind of putting it all together. If If I had that, now this one actually has a name. My a here is 2. So if this is my basic graph, right, we start at 0. I'm going to go 2 above it. That's what I cross. This is a decay. So it looks like this. And then keep on going. Right, so that's how it normally looks. What do we got to do to it? We got to move it down 4. So that's going to make my vertical asymptote -4, and then we're going to move it right 3. So let's do that. So my horizontal asymptote, that might have said vertical, I'm sorry. It should be horizontal. Y equals -4. Like that. Now my a is 2, so we're going to go 2 above that. So right here would be my normal, exit y-intercept, but we got to move it right 3. So 1, 2, 3, right here is where my actual point is. Then we graph it and look something like this. Again, it's a sketch. If we're trying to be like a fancier graph, we could find the x and y intercepts. But right now we're just trying to sketch it. So it looks something like that. Okay, let's talk about the natural base. So e is a very special number in mathematics. It's an irrational number, right? So it never ends. So it's 2.71828 blah 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 blah. Keeps on going. It has a very special properties of mathematics. We mostly use it to solve exponential equations. So that's e. And if we ever want to graph e, well, e is just a number, right? So if I give you y equals e to the x, this is just going to be a growth because it's bigger than 1. Because e is a number, 2.71828 blah 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 blah. So we graph it just like an exponential, just like a growth graph. Like that, right? We have an asymptote right here. It crosses at 0, 1 and goes on. So let's look at e real quick. So first is use a calculator to evaluate the function e to the x. All we have to do here is substitute it in e to the -2 and type that into your calculator. Here's my calculator. And we're going to do e, so second right here, and then to the -2 power. And you get the number, 1.35-ish. Well, it keeps on going. Like that. And that's all it is, right? E is just a number. Don't be scared with it. If we were going to graph it, like I said before, it's just a growth. So plus 0. My a is 1. So we're going to cross that 1. My horizontal asymptote is at y equals 0. Like this. And then it is a growth graph. So it's going to grow from here to here. So it looks like that. If we're going to graph e to the -x, well, same issue, right? So plus 0. So here's my asymptote. We'll normally cross that 1. I'm going to graph the first one originally first. It looks like this. That's e to the x. And then what does this guy do? Right? It's on the inside, so that's a horizontal flip. We're going to flip this thing horizontal. So we're going to flip it this way, right? We're going to flip it left and right. So it looks like this. And that's e to the -x. Right, so e is just a growth graph. That's all it is. It has special properties of mathematics, and we're going to talk about some of those, but graphing it, just the same. I guess I had one more. 3e to the x plus 4. Okay, so look at my a, it's 3. It's plus 0, so my horizontal asymptote is still the same. Y equals 0. Like that. My a is 3, so we're going to go up 3. So like right there. Now normally I would draw a growth from here. So I'm going to go from here and go up. That's what it normally looks like. And you can kind of see what the 3 does. Right? As you can see, like it expands the graph a little higher. But we have to move it left 4. So that point is actually left 4 right here. That point moves to right there. Right, so we'll move that point over here, left 4. That's where I'm going to do the exact same graph. I'm kind of go on the floor and I'm going to expand up here. So kind of like this. Probably started way too far back. Something like that. Again, we're just doing a sketch, so it looks something like that. If I wanted to, we could find the y-intercept. We plug in 0 for x and get a value. You get a final y-intercept. But that's the general idea. Okay, let's do some applications of e. So we use it a lot in interest and compound interest. In continuous compounding interest. So compound interest, you might have seen this before. A equals p 1 plus r of n to the nt. Let's talk about what it means. This is the formula. P is printable. That's like deposit. So it's like your deposit. It's your initial value. Annual interest rate, R is just the rate. So R is the rate. T T is years, and then N for this one, N is the number of times compounded. Compounds, how many times like they calculate interest per year. So if it's like yearly, N equals 1. If it's like monthly, N equals 12. Quarterly, N will equal 4. So it's like that. When we compound it continuously, we use this form, asymptotes. It's like the shorthand, right? We're going to use our e to the RT power and p. So it's a lot more, it's a simpler formula. Like you don't have to like do more stuff. It's printable, it's a rate in the time. And since it compounds continuously, we use this formula. So let's do a couple examples real quick. A total of $9,000 invested in an annual interest rate of 2.5%, compounded annually. Find the balance after 5 years. Compounded annually. So we're going to use a compound interest formula, and n equals 1. So we're using this one. So I'll put the formula down. A equals P, 1 plus R over N to the NT. Right? So 5 years is our T. So that goes here. Compounding annually, so N is 1 and 1. R rate. Now this is in, we got to make it a decimal. So 0.025. We're going to move over 2 spots to make it a decimal. And then we put $9,000 in. So like that. So if, I guess I should write it like nicely. So 9,000, 1 plus 0.025 over 1 to the 1 times 5. If we get our calculator back up, so I'm going to put 9,000, 1 plus 0.025 divided by 1 to the 1 times 5 power. So we get, roughly now get us money, so I'm going to round it to the nearest dollar. 182.67. It's about 10 grand. So in those 5 years, we made, no, again, we started with 9,000. We made about over $1,000 in those 5 years. So next problem, a total of $12,000 invested in an annual interest rate of 3%. Find the balance after 4 years for each compound type. So A is quarterly. So A, we're going to use the exact same formula. A to the P, 1 plus R over N to the NT. Right, our R here is 0.03, and we make it a decimal. N is quarterly, which is, N is 4. So 4 goes here, 4 goes here. We're going to do 4 years. We started with $12,000. So I'll put all that in the calculator, we'll get an answer. I'll just do it off screen to save some time. And I get 13,523.91. Right, nearest dollar, we're doing money. So that's compounded quarterly. Now let's do it continuously. Formula's a lot simpler. It's asymptotes, AP e to the RT. So we're just going to plug in our initial, 12,000, E, and then 4 to the 4. Sorry, is it 4 years? Sorry, rate, my mistake. 0.03 to the 4th, sorry about that. Right, R is rate. And we put that into our calculator. That one I'll show you because that's a new one. So 12,000. And then second E right here. And then 0.03 times 4. So we get 13,529. And I didn't count the cents. 96 cents. So you can see it's a little bit more money if you make it, which over time adds up. So continuous is generally the way you want to go. So you make more money that way. Okay. Radioactive decay, let Y represent a mass in grams for radioactive strontium, that right there, whose half-life is 29 years. So half-life means how long until you have half the initial. Right, half its life. So that's what that means. Half-life, you have a radioactive substance, it starts with a certain amount. How long does it take to get to halfway that? And then, so the quantity is represented in years as this. So here's the formula. What is the mass initial mass? What is initial mass when T equals 0? They tell you T equals 0. Just plug it in. So it's going to be Y equals 10 to the 1/2, 0 over 29. 0 to anything is 0. So 10 to the 1/2 to the 0. Anything to the 0 power is 1. So I get 10. So 10 is the initial weight in grams. How much of the initial mass is present after 80 years? So after 80 years, so that's our time. So we're going to substitute in 80. So you just go Y equals 10. So 1/2, 80 over 29. And then we substitute that in the calculator. So 10 times 1/2 to the 80 divided by 29. You get about 1.47. 48 if I round. So that's how many grams are left after 80 years. So again, half-life in general just means how long it takes for it to reach half its amount. That's what do the formula right there. But other than that, we're just like substituting in, right? Reading the problem, substitute in. Eventually, we'll discover half-life in a future lesson. Okay, last one here. The approximate number of fruit flies in an experimental population after T hours is given by this. So you can tell we're doing an exponential function here, and it's telling you the number of fruit flies over time. Find the initial number of fruit flies. Initial is always time equals 0. So here we're going to do the same thing. My Q initial, we're just going to plug in 0. Anything times 0 is 0, so we get 20 e to the 0, which is just 1. A to the 0 power is 1, so you just get 20. In general, it's always like the A is always your initial. So anyway, we have that many fruit flies. So 20 fruit flies. B, how large is the population of fruit flies after 72 hours? So same idea, but now we're just going to plug it in. So Q of 20, 72 hours, sorry. 20 e to the 0.0372. So we're going to plug that into the calculator. So 20 e, there you go, 0.03 times 72. 72. You want to say 22. So I get 173.4. I get for talking about fruit flies, probably just round it to 173. You can have a half a fruit fly. Like that. And then last thing, they want us to graph Q. So graph that, don't be scared, it's like a normal thing. So how do I graph that? Let's do it. I'm going to do a big old graph right here. Right, so first, initial horizontal asymptotes at 0. So right there. What's my A? My A here is 20. So remember, that means you're going to cross that 20 above. Right, your A is always initial, like your initial y-intercept. 0.03t is like a horizontal shrink. Or actually, horizontal expansion, actually, in this case. Because remember, you do the opposite. You're going to times everything by... You're going to divide everything by 0.03, which makes it bigger. But again, it's just a sketch. So unless you want to put in your calculator, it's just going to be a sketch. It's going to be a growth. Because E is a growth graph, right? It's bigger than 1. So you get something to that effect. If we're going to do it by hand, you get something to that effect. If you're doing it with the calculator, you just type it in. Anyway, that's the lesson.